All right, let's get started. Pretty simple plan for today. We're going to be doing a little bit of Python for the next 4 lessons, which is a great programming language. And then we'll be moving into RNA-seq analysis. So that's our plan for the next few weeks. Any questions? I have another homework that's due. We're going to do the homework a little differently. So it's here, and just in case, I tend to go over on the labs and then scrambling to find a good stopping point. So we'll talk about the homework first so I don't forget. Homework 5. So we're going to be learning how to write code today. And so what I've done is I've written a script and it is almost all comments. And your job will be to go through and add the bits of code that do what the comments say it should be doing. And all of this will hopefully become pretty clear after the lesson. There's one area where I went ahead and gave you the piece of code because we're not really going to go over this. But everywhere else, you start with some strings. And then each place it says point value, something goes after that. You need to put something there to get your points. And I gave you some example output using different input strings. So your example output should look very similar to this, but not exactly. And I will, what I want you to do is write your code, test it on the ACF, or for those of you who have Python installed, you can test it on your own computer, and send me the code as an email attachment in plain text. Do not send me a docx. I will not open it. Do not send me a docx. I'll say it again. Plain text. So if you're on an Apple, something like TextEdit. If you're on Windows, you should be able to use something like Notepad and save it as a .txt, even though you'll probably be testing it as a .py. For the sake of your laptop and for email attachments, just use .txt, make sure it is plain text. I will copy and paste it and run it and expect to see this output. I'll also be checking to make sure you didn't hard code anything in there to just spit out the output that you want to see. You need to actually have the logic that I asked for. So don't think you can get away with that. So that's the plan for homework 5. That's not due until next Wednesday at midnight, and just email it to me instead of trying to deal with Canvas this time. Okay. So I do want to tell you a little bit about Python before we start learning Python, because I want you to feel like you're not wasting your time. And it's actually a pretty interesting language that's pretty fun to learn about. So you remember, similar to the software carpentry, where we first went online and we kind of did the lessons provided online by Software Carpentry, we're going to be doing the same thing with Python. There is this great book called Python for Biologists. It is really just the most approachable, fantastic book for learning Python, and every single example is relevant to biology. So I think that makes it very accessible for your average person. We're only going to make it through the first 4 or 5 chapters, which the author does make available free online. So you don't have to buy this. I try to make the course such that I feel like you're already paying tuition, or somebody is paying tuition on your behalf. You shouldn't necessarily be investing any of your own personal money. People who don't have enough money should not be penalized because they can't afford textbooks. So you'll never be asked to buy anything in this class. But if you were thinking of buying something and you want to go further with your education, it's a great book. It's $39 on the Python for Biologists website or on Amazon. And the author has produced actually a whole series of books. So Python for Biologists, Advanced Python for Biologists, and Effective Python Development for Biologists. I have not bought the last one, the purple one, yet. So I don't know what's in it. But he did a really good job on the first 2. And if you were thinking about buying the bundle, it's worth it to go ahead and buy all 3, because you can get them for $99. Whereas if you buy them piecemeal, it ends up costing you $120. So you can save about $20 by buying them as a bundle. If you're in a lab and you think multiple people would like to use this as a resource, it might be worth trying to convince your PI to just buy a set and put it in the lab. So yeah, really, Martin Jones is the author. He does a really good job. There has been significant debate amongst people who teach bioinformatics at this university about what programming language should we be teaching students? What's the right language to learn? And this is in the introduction to the book, and I completely and totally agree with it. This is a surprisingly unimportant question. This is not the right question. nearly everyone who programs professionally uses more than one language. So it really doesn't matter which one you start with, because you will, before long, have to learn a new one. Also, learning one programming language gets you about 90% of the way to learning another programming language. So the hard hill to climb is programming language number 1. After that, it gets easier. And that's because programming is just a way of thinking. It's a way of being able to take a problem and break it into little tiny steps that you can teach a computer how to do. The syntax, like the actual way that you write the code, is kind of a very minor part of that. It is something you end up having to memorize or look up, but that's not the hard part. The hard part is learning how to think about a problem in a way that you can teach a computer to do it for you. And you have to learn that for any programming language. So whichever one you picked, you'd have to learn that. And the third one, most of the problems, and certainly the problems we conquer in this class, are solvable by any programming language. It's not like, oh, C can't do that, or oh, Java can't do that. It turns out that like at the basic level, most of what we're going to be doing could be solved in any language. So what is important if you're going to learn a language? Putting in the time. This is not something that we're going to do a whole lot of justice to in 4 class periods. If you want to become a really good programmer, I'm thinking, 2 or 3 classes would be a good starting point. And if you're doing it on your own, that's fine, that's great. I actually know lots of biologists who've taught themselves to code, but you need to be investing those hours, investing the time in it. Intrinsic motivation. It's not always easy. You have to be the kind of person who likes to solve problems, who isn't daunted when you get errors, who is really motivated. Having colleagues around you that can help is super, super, super important. In my lab, you're welcome to come hang out. I've got a couple people who do Python. I've got somebody who's a really spectacular R programmer, and then I have some people who do primarily PHP and JavaScript. So if you wanted to get into web development, but it turns out any of them could help you probably with your basic problems. So if you're in a lab and no one around you can help you like get over your problems, let me know. You can come sit in my lab. We're teaching undergraduates to program right now. It's super fun. But just because when you get stuck on that problem that would take you 6 hours to solve, if there's someone right there that could help you solve it in 60 seconds, it's just going to make a huge difference for your learning curve. And the final thing I think is important when learning a programming language is trying to solve real problems. I love Python for Biologists. I think it's a great book. I want you guys to really love it. But if you just follow the examples in the book and type them in the computer, you're not actually going to know how to program. When you have your own problem that's really hard to solve, and it's not the perfect example that's already in the book, that's when the real learning begins. So go into, like, maybe while you're reading the book, think about having a real world problem that you're trying to solve. And start thinking about, like, how would I use these tools to do this other thing? Like, what techniques could I apply? So that's really helps you to like evolve your thinking to becoming a real programmer. So with only 4 lessons, I would call this more of a teaser than like an actual learning a language. But here are my goals. I want you to understand what it means to write code and execute scripts. So when you see somebody else doing it, you know what they're doing and kind of how it works. Maybe this is not something you're going to be doing a lot of, but you have like a basic understanding of how this works. Understanding how programmers break problems into instructions. Understanding that, like, oh, if I describe this to a colleague who is going to write some code, I need to walk them through this in a very stepwise manner. How could this problem be broken up? And both of those kind of go into communicating with your bioinformatics colleagues. Many of you may become more bench scientists in the future. That might be your primary endeavor, but you have colleagues who are going to be like writing a lot of code and helping you to solve problems. Being able to communicate with them means you need some basic understanding of what they do. And finally, being able to use scripts. So maybe you're to the point at the end of this where you can go find a publicly available Python script on the internet and download it and run it. You might even get to the point where you could debug or alter a script to do what you need. I'm not confident that with the small amount we're going to do in this class, you can go out and just write scripts from scratch. But if you're motivated and you're interested and you put the time in, you probably could. But those are our initial goals. Lots of people ask me what other classes they can take after they get this kind of like, either you're going to love Python or you're going to totally hate Python. And if you love it, you may think, oh, I really want to learn more. So there's a Life Science 507, Programming for Statistical and Graphical Analysis of Biological Data. It is a Python-driven class. The lab is 100% Python, and they go much, much, much further than this class. My student is TAing it right now, and they get a lot done in that class. It looks really fun. Is anyone taking that right now? No. I think it's going to be a core requirement for genome science and technology students in the future. But this is the current version, the way it's being taught with all Python as the lab, I think is the first time this year with TN. There's also, if you're more of an R person, so R is probably more common in ecology or environmental biology as opposed to genomics. So a lot of people learn R. There's a geology class, I think it's taught by a professor in Earth and Planetary Science. And it's called Introduction to Reproducible Data Analysis. It has an entire R lab. You'll get a lot of R. It's great. There's a new, and this last one I don't know a ton about, Introduction to Programming. It's taught out of the computer science department. I think they do a survey of like 3 languages. So it's more of a shotgun approach to learning a little bit about a lot of languages. That'd probably be the last one that I would pick. I think you're better off sticking with one language to start and really trying to develop some skills. After you have one full semester of programming, Scott Emmerich is teaching, right now it's a special topics. I think it's gonna become like a named course next year. So just look for Emmerich as the professor in computer science. This is, you walk in and like homework day 1 is like write a program that does this thing. So you need to have like some real programming skills under your belt. So that's my warning. This class may not be enough to really be an appropriate prerequisite for Scott's class, but you can always go talk to him about that. Also, over the course of the this past summer, all of the people at UT who teach in the bioinformatics realm have gotten together and helped to create kind of this curated class list of all of your options for furthering your bioinformatics education. So I thought I'd point you at that if you're starting to think about registering for next semester. Okay, so I've told you that it's not important what programming language we pick, but we picked Python, or I picked Python. And why did I pick that one? Python there's actually been some empirical studies about the easiest language to learn. And Python has consistently been at the top of the list, if not the #1 language. It has a very consistent syntax. So unlike when you learn English and there's a million exceptions to every like quote unquote rule, and there's lots of special cases, Python tries to be very, very consistent. So when you learn a rule, it should hold for everything. There's not lots of edge cases and things that are gonna be different in this case and not in that case. It's pretty consistent, so that makes it easier to learn. There are tons of built-in libraries, which means you can go out and get code that other people have written that does what you need it to do without having to start from scratch. That's really nice. It's like when you have a laptop and you don't want to write your own word processor, you just go download Microsoft Word, and now you have a word processor. It's very much like that. You go get the modules and the code and the software packages you need and bring them in. It is one of the most widely used languages in the world, so it's a good one for applying for jobs and putting on your CV. That also means when you Google problems, you will generally find pretty good answers and lots of people who have chimed in, and that's important. You want to be able to get on the internet and get lots of advice and go to tutorials and look at documentation. It's easy to get started. It's designed in a way that lets you really write useful programs early. There are other programming languages where you have to learn quite a bit before you can ever get them to do anything, which is frustrating. So this one we should actually have be able to write code that does things you might care about by the end of today. We're going to talk a little bit next class period about white space and Python. Python and white space have a very interesting relationship, and it's something you'll have to wrap your head around. So it is annoying, it is hard when you first get started, but it can be good for beginners as it enforces a certain amount of readability. And one of the goals with Python is to be able to look at it as though it's like English and to read it and be able to actually read what it's doing. How well it actually achieved that is debatable, but it is better than some other languages. It is widely used for biology. So in particular, the biology community has really embraced Python. So that's another good reason for you guys to learn it. Many of the libraries have been designed by biologists to do various biology type things and statistics. There's some really good statistics libraries, which are really great. And Python's really good for manipulating strings. And we'll talk about, I think I've mentioned strings are characters, sequences of characters. And we particularly care about text as biologists because we're also often working with sequence data or protein data or a file format, like something that's come out of a piece of software and we need to manipulate it. Again, if you're an ecologist or an environmental biologist or a chemist, you may be working with more numerical data, things that live in data frames or matrices. You might want to look at R. I mean, Python's actually pretty good for that too. But for us, we're kind of coming at this from, I have a lot of text that I need to process, and Python's good at that. You may have originally heard Perl was the language to learn for bioinformatics, and it was for a very long time. When I went through school, I graduated with my PhD in 2007, and we were 100% Perl lab. And there was this huge shift. Like as soon as I graduated, everybody was like, no more Perl, Python. I was like, wait a second. I've been graduated for a year. We're already changing everything. So that'll happen to you too. So get ready. But Python is the current hot thing. And the switch has been low barrier to entry and efficiency in writing code. People really wanted something that was easier to teach, easier to write the code, easier for graduate students to pick up quickly. And that's just really important to biologists because many of us, our primary day job is not writing code. So it needs to be easy to do. Python has an emphasis on readability and simplicity. There's a study that is actually a few empirical investigations that say it's easier to learn than Perl. And I think it's trendy. I mean, there's something to be said for like, just like fashion or just like other things, like we go through trends, and right now Python's kind of a trendy language. So that turns out to be kind of important as to what people use. But if you learn Python, the leap to Perl is very short. They're very close syntactically. They're not like the leap from Python to Java or Python to C or Python to JavaScript would be much further. Python to Perl is a pretty close leap. So if you end up needing to learn Perl for whatever reason, your lab has a bunch of legacy code or whatever, it's not too bad. So the real debate now is Python versus R. Which one should you be learning? As I mentioned, learning one language makes it easier to learn a second language. However, the syntax between Python and R is quite different. So while you learn how to think in Python, the approaches in R can be very much more different. But if you learn to think like a programmer, you should be able to make the leap. R is something you might want to consider if you're focused more on statistics and graphical models. If you're looking at data science as a career or being a statistician, R is going to serve you better. It's always been centered in academics and research, less so in industry. So in industry, they all use like SAS, SAS, and SPSS. And anyway, I don't mess with any of that. But if you're looking at industry, there's a whole different set of languages. And there's this really funny like infographic, the data science wars, where they like pit R and Python against each other and go through like a whole bunch of ways that they're similar and ways that they're different and which one should you pick. And the take-home message is it's kind of up to you what you need. And they recommend looking at what problems you want to solve. And I would follow this up with saying, what problems do you want to solve and have they already been solved? And if so, what language are they solved in? Learn that language. Or something tangential to your problem been solved similarly in that language, because then you can build off of that code. What are the net costs for learning a language? Staying with the system you know versus learning something new. What is the time investment? What are the commonly used tools in your field, which means you'll be able to leverage other people's codes. It also means that you can get a job, which is important. And how do the tools in your field relate to the other commonly used tools that you need? So kind of big questions, hard to answer if you're not familiar with the field. If you have questions, let me know. But those are the kind of questions you want to be asking about where to invest your time moving forward after this class. This was a survey looking at, I think this is based on job postings. What are people looking for the most? Python came up 4th, which is not too bad. R was 14th and Perl was 16th in the rankings. So Python is definitely trending upward and is what a lot of employers are looking for. Looking at open source code, which is primarily where a lot of our research and academic code is open source. And GitHub is this huge open source code repository. I use it to teach the class out of, but that's a very non-traditional use of GitHub. It's normally for code. And in this world, Python is actually second. And R and Perl didn't even make the top 15. So I think that gives you an indication of why we're going to learn Python. So here's some history of Python. It was created by Guido van Rossum. He first released it in 1991. And it's kind of interesting. The origin story for this language was, I'm taking a week off for Christmas and I don't really know, I think I need a little like pet project to keep me occupied over the holidays. So I'm going to write a new programming language. Like, really? That's like a big pet project. But it's now sort of the development is steered by the Python Software Foundation, but they have elected Guido the benevolent dictator for life of Python. So he's still kind of in charge, and everybody pretty much loves him and thinks what he does is great, usually. He named Python after Monty Python and the Flying Circus, which if you're not familiar is this British sketch comedy series. And so it's kind of a funny name, and everybody, I think that's pretty memorable. Most people think it's named after the steak, but it's not. And Guido had this whole like design philosophy. He has this very like this artistic vision for programming languages. And actually the next slide is better. So here this thing called EPP622, the Zen of Python. And Python has 20 aphorisms, just like a religion, of which 19 are written down. So this is very Monty Python-esque, like kind of funny. But the aphorisms include beautiful is better than ugly. Your code should be beautiful. Simple is better than complex. If you can do something more simply, you should always do it that way. Complex is better than complicated. So if you don't have a choice, as simple as possible is where you want to go. Readability counts. So making sure your code is readable, making sure Python as a language stays readable is a very important thing. Special cases aren't special enough to break the rules. This goes back to like the core philosophy of Python is consistency. Just because you've come up with some great special case, that's not, in general, in Python, that is not good enough to break the rules. You need to stay consistent. And if the implementation is hard to explain, it's a bad idea. So these are kind of like, he came into this programming language just like, we're going to make something that is just beautiful and simple and makes everybody really happy to program in it. So here's some online resources that are really helpful. The Python Software Foundation has downloads for Python if you want to install it on your laptop. Installation instructions as well. Tons of documentation in many, many languages. And a Python for Beginners tutorial that is not biology-based, but it's still pretty good. There's also a Python package index, which is the official repository for Python software packages. So if you're going out and looking for maybe somebody who's written the code to do what I need already, that would be awesome. This is where you want to go check. There's more than 49,000 packages. People call it PyPy. So if you hear that, that's what that means. The one thing that has been very controversial about Python, and I actually think Python might have taken over the world by now, except for this one messy thing. There's this transition going on between Python 2 and 3. Python 3.7 is the current stable release. That's the release we'll be using. It was released in 2008, and you would think in 10 years they had sorted this transition out, but you would be wrong. It is shiny and new and beautiful and does many wonderful things. However, what they did that caused the big problem is that it is not backward compatible with version 2. So if you install version 3 and you have thousands of lines of Python 2 code, they don't work anymore, which is a really, really big problem because a lot of people were programming in Python. And most people who've spent years of their life writing Python code didn't really want to start all over. You don't actually have to start all over. It's a bit messy to transition from Python 2 to 3, but certainly not impossible. And it's not like you're starting completely from scratch, but a lot of people just didn't want to do it. And so there's actually still like more than half of the Python code in the world is still in Python 2 and hasn't been updated. So really just like super, super, super slowed down development in Python. And many people continued to program in Python 2 for years and years, even after Python 3 came out. And many people then didn't want to start new projects in Python because they were like, do I start with Python 2 or do I start with Python 3? I don't know, I'm just going to use something else. So this was definitely a debacle. 2.7 is still out there. You'll see it is still the default version on the ACF. Even though the final version of 2.7, well, the final 2 version was released in 2010. They are no longer updating it. They are, however, providing like basic support for bugs and for just security. But a lot of existing code has never been upgraded. So that's kind of the big problem with Python 2 and 3. And if you're looking for old code, you need to be aware that some of it's Python 2 and some of it's Python 3. And if it's 2, it won't work in 3. 3, it won't work in 2. And it's just a big kind of disaster. So what does it mean to be backwards compatible? This is a good thing to understand. Software programming languages that can successfully use the interfaces and data from earlier versions are termed backward compatible. So if all of the code in 3 could be run in 2 successfully, that would be backwards compatible. So basically interoperable with an older system. The benefits of backwards compatibility is that users can continue to use old code and data, which is helpful. We don't want to break everything every time we update a software package. And it makes it really easy to upgrade because you aren't breaking things. But the disadvantage, and this is why the Python people thought it was really worth it to just break everything, is they no longer wanted to maintain legacy features. They felt like some of the features that had crept into the Python code base were not, they didn't meet the high standards of Python. And they don't want to maintain them anymore. You're stuck with increased complexity. You're stuck maintaining everything that's ever been written. And you can't throw it away, which is frustrating. And it slows innovation. So Python, between the 2 to 3 transition, they decided it was worth it to go ahead and break backwards compatibility to get the advantages. So 10 years later, you're still dealing with the fallout from that decision. But Python, so we're going to learn 3. We're just going to start with the new code. And I think most people are now teaching 3. And this is becoming a less of an issue with every passing year, especially as a lot of the old legacy code gets upgraded. But be really hyper aware when you're Googling and you're looking at documentation, if the documentation is talking about Python 2 or Python 3. And if you're Googling a problem or searching for a problem, put Python 3, put the number 3 in the search to try to help land on things that are Python 3. So here's a little graphic I found online looking at 2 versus 3. Some of the major things they did, they went from an ASCII text to Unicode text. And this is like a really fundamental change in how you store characters in a computer. So this is one of those things that like broke a lot of code. But Unicode's great because Unicode is a much larger expanded set of characters. You can have special characters from other languages. You can have like all of the emojis have Unicode codes. And so it just really vastly expands things that you can store as text. Whereas ASCII is very much limited to English letters and numbers. They changed how division works. Which again, when you change how division works, that breaks a lot of code. And this is the Perl way of doing things. There are other programming languages that work this way. And it was because computers used to be like slow and not have a lot of significant digits. But so if you divide 5 by 2, it tells you the answer is 2, which is kind of dumb. But basically what it's doing is it's giving you the integer, and then you have to do another operation to get the fractional component. So you would have to do 5 divided by 2 to get the integer part, which is the 2, and then 5% 2 to get the fractional component, which would be the half. And in Python, they just went ahead and fixed that. So that when you do 5 divided by 2, you get 2.5, which is, as a scientist, what you would hope and expect for. This is a huge gotcha in like Perl, and I think C works this way too. And it's just legacy based on like how computers worked and how they were programmed in the 70s. So they updated that, which is great. The other thing is print was like this really famous exception that broke the like beautiful Python consistency, and that you didn't have to use parentheses when you use the print function. Every function we learned in this class uses parentheses. And they had this one function that didn't need parentheses. And they said, no, we have to go back to our core basic values. We do not break rules. So now you have it, but previously there was lots of code in the world that printed out error messages or printed out messages, and all of it has to be fixed to use parentheses. So when I say that they did a really, like, this was a significant transition. These are things that are very fixable in code, but it just takes time. So we aren't going to see any of these packages in this class, which is super sad because they're awesome and things you should look at. NumPy is great. It's a scientific computing package. Large dimensional arrays. So what do I mean by large dimensional arrays? If your research produces vast Excel spreadsheets that are difficult to manipulate and subset and filter, and you would like to be doing something with them that makes more sense than Excel, NumPy is for you. It also does a lot of mathy stuff, so linear algebra, Fourier transforms, random numbers. And upgrading from NumPy, again, if you have like really big Excel file, like matrix kind of data, Pandas is really nice. And I would say Pandas operates almost kind of like R. So if you're an R person and you're looking for the equivalent in Python, R can be quite slow. R is not super efficient. So if you're looking for the R type functionality and something a little faster, Pandas. And then we will see, hopefully we'll get to BioPython before it's all over. Which is very essential bioinformatics support for Python. Importing sequences, dealing with FASTA files, converting between different file formats. They've already written tons of that for you, which is so nice. So we're gonna see a little bit of that. Python is available on the module system on ACF. So if you type module avail Python, you're gonna get a whole bunch of options. The default is 2.7.13. I think that's crazy. I don't know why the default is still 2, but they have 3.6.1 available. You can also do this module load Python 3. And so then if you type Python on the command line, it uses Python 2, but if you type Python 3, it uses 3, so that you can use them both interchangeably. You'll also see this stuff called Conda, and I want to talk a little bit about what Conda means. Conda is short for Anaconda, which is a play on Python. It's a distribution of Python that has all these tools to manage packages and dependencies and environments. So basically, if you want to log into the ACF and get Python 3, and you want to have BioPython, and you want to have NumPy, and you want to have Pandas, and you don't know how to install any of that, you install Anaconda, and it helps you manage all of that in this really simple, straightforward way. It's really useful specifically on the ACF because you don't have admin access. So you're not a root user, you're not the owner of the ACF. So it can be difficult to install things, and this is gonna make it really easy to install things, and it's gonna install them into your own user space where you have permissions. So that's what I think we're still debating, because we're still working on writing the RNA-seq labs, but Narula may use Conda for some of the packages that we're gonna use in RNA-seq. So I think you guys might see it. We use it in my lab to install all of our Python packages. That's how we manage it. Okay, so before we get into the lab, I want to do a little bit of background. Python has different data types. These are just a very small number of the data types. But these are the ones that I think are the most important to understand. So integers are exactly like they are in math. The shorthand in Python is int, int. And these are numbers that do not carry a fractional representation. Just simple integers, no fractional amount. If you want fractions, it's actually called a floating point number. So a float is the abbreviation. So these are handled differently in the language. So it's worth being aware that, and this is how originally we came up with that division problem with you take an integer and you divide by an integer and you expect an integer back. Well, what if there's a fraction? That's a floating point number. So you have now changed the data type of what you're working with. And we'll see a little bit of that. Floating points also can use the scientific notation using the E. Boolean is something that you'll see in all programming languages. The shorthand is bool, B-O-O-L. This is a representation of true and false. And the keywords, it can only be true or false. Those are the only two things a Boolean, well, I think it'd be true, false, or null. It can not have a value. But Booleans always represent kind of a binary true false variable. And finally, strings. And strings are abbreviated STR, stir. And strings are sequences of characters. So I have a whole slide on strings. Let's move on to that. So it's a sequence of characters, or a string of characters, right? Like that's how it got its name in English. I've got a string of things, a string of characters, so it's called a string. And you'll see this term string literal a lot in the Python documentation. So it's a representation of sequences of characters in source code. And this gets a little meta because you're using characters to talk about, to like communicate, like you're writing characters, like the Python code is itself characters, but you're also thinking about being able to have characters as like a data type that you can manipulate. So what's the difference between the characters you're just typing this code versus the characters that are the thing that's the string? So when they say string literal, that means that is a chunk of characters that I want to treat as an object. It's not code itself. It's something, it's like a number, or it's like something that I want to do something with. They're delimited by single quotes or double quotes. Either one is fine. You will also occasionally see triple single quotes, and we're not going to get into that. That's a whole other thing. It is a viable way to represent strings that has its own reasons you wouldn't want to do that. But we're not going to get anywhere close to needing to use that in this class. So single quotes or double quotes. And this, okay, this is a little bit of Python code. This is where we're headed. We have a comment, which we've already seen in our bash scripting. We have a print statement with our parentheses, because this is Python 3. And inside the print, this is a string. That the string is delimited by double quotes. And then below we have some mathy stuff. So when you're looking at this, and the comment's now hidden, but so there's all this characters on the screen, but they're different things. The blue part, or this is hold on. Okay, there we go. This is a comment. The blue stuff, that is not being read as Python code. It's a comment. It's after a hashtag or a pound sign if you're old like me. And the red stuff is code. That's actual Python is trying to interpret that as characters that mean do stuff. Whereas the green, this is a string, and that's like an object. And we have set those aside. Those are not being interpreted as Python code because they're in quotes. Does that make sense? Okay. And let me save that. And I'll try to remember to upload the fixed version of that to the website. Does it look messed up on the website? Is anyone following along? It's messed up? Okay, I'll try to remember to fix that. It's worth talking about different types of brackets and quotes, because especially people from international countries, your keyboards have all different, like keys are in different places and I can't find. So when I say parentheses, those are the arcing type of bracket. Square brackets are indeed make a little square, and curly brackets are the one with these like little swoopy part. So yeah, the vocabulary we use for that is parentheses, square brackets, curly brackets. Single quotes are the ones that are kind of arcing like a backslash, and double quotes are the ones that are kind of arcing like a backslash, but there's two of them. It is not the same if you hit this key twice as a double quote. Like there's an actual key that creates like two little marks at the same time. That's what you need for a double quote. Backticks or back quotes are going the other direction, and they are totally different and do something different, and do not use those for strings. They do not denote a string. They denote a system command, and you don't want to do that. So find these on your keyboard. And I wanted to talk a little bit about shell scripting. And it was really funny. So my husband is a programmer, and we were cooking dinner last night, and I was like, how do I explain to the class the difference between shell scripting and like a real programming language? And we got into this huge debate. We were trying to come up with analogies, and the only analogy we came up with was cooking related, probably because we're cooking. But so you've seen a little bit of shell scripting. And the question becomes, well, okay, A, why is shell scripting different than like Python? And why can't I just use shell scripting for everything? And why would I ever use it? Why did we learn it if we're going to learn Python? And the answer is shell scripting is really useful for basic tasks, especially if it's a command line task. If you need to automate a command line action, shell scripting is going to be fast, easy, and efficient. If you need to do file manipulations, in particular, if you need to run a piece of software on 100 files, or if you need to count the lines in a file. Shell scripting is excellent for that. It is, however, not for building software. It's not like a big, robust, kind of feature-rich language. It's kind of short and compact and efficient for what it does, but it's not big and bloated with a lot of features. There's not a lot of sophisticated data structures. There's not a lot of libraries out there, functionality. So you're not going to go out and find a bunch of like bash scripting libraries that do statistics for you. So the analogy I came up with is bash is like a microwave. If you have a bag of popcorn, that microwave is the perfect thing for that bag of popcorn. But if you need to cook dinner for 20 people, you need like a full kitchen stocked with all the equipment and all the accoutrements and everything you need. So that's the difference. Bash is like, it's worth learning because sometimes that's what you need. It's the right hammer for the job. But in many, many, many other instances, you need like a much more sophisticated approach. And that's what a real programming language like Python or R is going to give you. All right, and this is a comic from XKCD, and this is a great, super geeky computer sciencey comic strip, and I think this just completely sums up why people think Python is like the best and why Python has become really, really trendy. So I put that into the slides for you guys. Everyone thinks Python is like, you just type a thing and it happens and it's amazing. So that's what the comic's about. Okay, so the next thing we're going to do is log on to the ACF and actually do some Pythoning. So I'm going to go ahead and go to our class project directory. We're not going to be working with big enough files for it to matter for us to queue sub, though. I think we can do this lesson fine on the login node because we're not going to be doing anything very sophisticated yet. I'm going to go to our course directory. Again, please put your user ID there. And I might name it something like Python practice. Now I've got a nice new empty directory. So let's check out our modules. Module avail Python. So these are all our options. We're going to learn Python 3, and I don't really want to type the 3 every time, so I'm going to do module. Okay, well, before we do that, let's see what version of Python we have. So I do Python -- version, I think is how you do that. The default on the ACF is 2.7.5. So we don't want to work with that. We want to work with a different version. So we're going to do module load '361. And now if I do Python version, it should tell me 361. So anytime you're confused and you're not sure what version of Python you're using, just type Python -- version and it will tell you. Okay, so let's write our first program. Use nano, we'll call it hello.py. So the suffix for Python code is usually .py. PL is Perl, SH is bash scripting, so they all have like their own little common shorthands. And a very traditional, since the 70s, first computer program to write is hello world. We're gonna do print hello world. Okay, so before we run this, let's learn some vocabulary. This entire line is called a statement. So the statement is a functional unit of Python code, and each line is a statement that Python is going to read and interpret. Print is the name of a function. So a function is a thing in the Python language that does something. It functions to do something. So we learned on the command line that arguments come after flags. Well, Python functions also take arguments. Arguments are inside the parentheses. So in this case, we have a string, hello world, that is the argument to the function print. Print is the function, inside of the parentheses is the argument. Our argument is a string called hello world. All right, so let's save that. Nope. Now we can type Python hello py. It says hello world. So we've written our very first Python program, and it takes that print statement. It says, okay, I have been told to print out hello world, and it prints it to the screen. And that is right behind my head, so let me make that a little shorter. Yeah, so we talked about quotes being important. And that we can also use single quotes, and it should work just fine. So in this case, I'm going to replace the double quotes, do the same line again with single quotes, and I'm going to save that. And we get the exact same output. So whether you use single quotes or double quotes, identical. But there is an occasion sometimes that you want quotes in your output. So what do you do about that? How do you actually get a quote inside of your string? In that case, you can use the other quote. So in this case, if we wanted, we have double quotes on the outside. That means we're allowed to use single quotes inside. So we could put, maybe I'll put something like this. And ditto with the single quotes. If you have single quotes as your kind of delimiting string characters, you can use double quotes inside. You could say, so it's Python's reading it. Once it sees a double quote, it says, okay, this is a string that I do not interpret until I see the next double quote, right? So everything in between is fair game to be printed to the screen. Does that make sense? So that means single quotes are okay because it starts with a double quote and it says, okay, everything is a string until I see another double quote. So let me write that and save it. Oops. And in this case, we're getting our single quotes and our double quotes printed. So our strings are still functional. Comments work just like we've already seen, which is great news, right? It's great when something is consistent. This is a comment. It will be ignored by a computer. So comments are great, as we've already learned. We can put what code is doing. So we could say print a friendly greeting. And none of this is going to get printed to the screen, which I will prove to you. If that didn't change our output at all, those comments got completely ignored. So comments are great for other people if you share your code, because you can explain like how you did something or what you did, or if it's a particularly hard to read bit of code, you can say, oh, what I'm trying to do here is this. It's also good for you when you go back. We've talked a lot about it in this class documentation. It's not just for other people, it's for you too. It's for future you. Future you who has forgotten everything you've done 6 months ago. So give yourself a little memory jog. Like, oh, here I was trying to do this. That's like what comments are really useful for. And you will thank yourself in 6 months or a year or 2 years when you go back to some old code and you're trying to figure out what it does. The more comments you have left yourself, the happier you will be. And then also another thing, if you're updating code and you're changing it, update and change the comments too. That's a good idea. Let's look at some error messages. So I'm gonna actually just delete everything and start with clean slate. Again, this is all in this free tutorial online. You're not gonna lose any of this material. It's all there. What if we forgot our quotes? It's like a reasonable statement, might forget your quotes, be like, yeah, that should work. It should print whatever's inside the parentheses, right? Okay, so this is our first Python error message. First of all, it's gonna tell you the file. We're only working with a single file right now, so that seems kind of obvious where the error is, but if the file is pulling code in from other libraries and other files that live in other locations, it can be really hard to hunt down where the error is happening. So the first thing it tries to tell you is what file produced this error. The second thing is it tells you which line produced the error. Again, this is really useful if you have 200 lines of code. It's going to try to point you, I failed at this line. And third, this is also really useful. It tries to actually give you an indication of where in the line that it failed. And then it tells you what type of failure it was. Syntax error, invalid syntax. So syntax is like the grammar of a programming language. It's trying to tell you, I don't understand what you said is not an appropriate statement. It is not it's not grammatically correct for me. And so in this case, that might be a little bit difficult to interpret, but you'd have to think about what does the print function expect? What is the print function? What is the grammar? What is the syntax of the print function? If you went and looked that up, you'd be like, okay, I need parentheses. I need quotes around my string. Computer programs never work the first time, almost never. So we're learning errors early because you will get to spend a lot of time with them. And even for these labs, I try to shield you guys from some of the difficulties of writing a lot of, whether it's the command line or the scripts. I spend a lot of time running 15 things that don't work before I finally get to the one line. Oh, okay, I have the flags and the arguments and everything all in the right place and it works now. And I think that's a good way to learn, because you need to see it work. You need to see what a working example looks like, because it's hard to debug when you don't know where you're headed. It's hard to get to where you're going if you don't know what that's supposed to look like. So that's part of it. But also don't be intimidated by errors, because you're gonna get errors all the time. And even professional programmers who program all day, every day, every time they run a piece of code for the first time, they're probably gonna get an error. Yeah. I was trying to write a for loop on the ACF to go through, I need to give you guys extra credit for that assembly, for the assembly, and I was gonna run every single K-mer value that everyone in the class had to see if I got the same values. And it took me 7 tries. I was so mad at myself. But that's just normal, even if you're experienced. So I just don't want you to get frustrated with errors, because they're gonna be a part of your life, which as biologists, I'm sure you guys are all fully aware of. Things fail all the time. So let's see another error. So let's add our quotes back in. But what if we misspelled the function name? We put paren instead of parent. This is the most common errors are usually just typos. You've just typed something incorrectly, because typing is hard. Save that. Okay, so new error. Name paren is not defined. So this is a pretty straightforward error. It's basically saying, I don't know what paren is. Go find me a word that I know. So you would be like, okay, well, I clearly mistyped something. I need to go add the T back to that. Okay, so let's talk about splitting a statement over 2 lines. There's something in the world of strings called special characters. And I'm going to change these. Actually, this is one of those things that I can remember how it works in Perl, but I can't remember how it works in Python. So the special character for a new line is /n. So that means stick a new line in the middle of my code. So, well, first, let's see, what if we just did this? What would happen? It's gonna say end of line while scanning string literal. See, I told you you'd run into string literal again. That means you started a string, I'm not interpreting it, I'm looking for the end of it, I got to the end of the line, I didn't find the end of the string, totally unacceptable, not gonna deal with it. So how would you get a new line into the middle of a string? So one of the ways is these special characters, which is /n is a special character for new line. In Perl, it only works with double quotes, not with single quotes. So let's give it a try and find out how it works with Python. Oh, it works in Python with both. Oh, good to know. The other thing we learned that I think will work fine, we learned in with our command line, that you can do, so that slash is called a escape character, and that basically means don't interpret the next thing as like in this case, it's a new line. It's saying don't interpret the new line as the end of a statement. Interpret it as a character. So I think this will actually work as well. Well, it didn't interpret the new line. It also didn't give you a new line. So sometimes you have to play around with these things. Yeah, the /n will always work to give you a new line. Another special character is the tab. So if you want to get a tab printed inside of a string, you have to put /t. So in this case, we should have a tab between hello and world. And we get a little bit of a bigger space. Tabs end up to be important if you have a lot of Excel data, if you have a lot of tab delimited things that you're trying to print out or pull in, knowing that the tab is a /t and it's much better than trying to type a tab because it's hard. And we'll learn about white space in Python. It's a whole thing. So just remember tabs, /t, that's your best bet. Okay, so now let's work on variables. So I'll just leave that there. So let's write a little comment. Store a DNA sequence in the variable my DNA. I'm so used to typing DNA in all caps. Okay, so we learned a little bit about variables with the for loop that we learned for shell scripting, for bash shell scripting. In this case, the variable is, once again, we're putting a name on a container, and we can put anything we want into that container. A variable is named variable because it is literally, it can vary. It can be variable things. So we're creating a container called my DNA. I'm going to be able to do things to my DNA. I can print it, I can get the links, I can add to it, I can do things to it. It's called my DNA, and I can put anything I want in that container. And it turns out like this sounds really esoteric, why are we learning this? But this is how computers work. You teach them to do one thing, but you have to be able to give them different input, give them different things to operate, to do that same procedure on the same thing over and over and over again. The way we do that is with variables. So in this case, we have a variable called my DNA. We are assigning it a string as its value. So my DNA is a variable representing the string ATCGGTA. And now, if we run this, nothing happens. Well, we didn't get an error. It's not a problem because we didn't get an error. But we stuck a thing in a variable. Okay, great. So what? Now we have to do something with it. Do we want to see it? Do we want to add to it? What do we want to do with that variable? So one thing we could do is print it out to the screen so we convince ourselves that it exists. So in this case, we're going to say print the string. And we don't have to put quotes because this is a variable name. This is not the string itself. This is the variable that represents the string. So we can say print this variable. The name of the variable is my_DNA. And now if I run it, it's going to print our string. So we put this into a thing called MyDNA, and then we printed the thing, and the computer remembered MyDNA represents the string ATCGGTA. So later, when we say print the thing, it says, oh yeah, I know what that thing is. That thing is the string. I've stored that, I remember that. That's what this variable means. We can change the value of a variable. We can assign it something else. And now the variable will represent a different thing. But order of operations matters. So let's save this. So it's still printing ATCGGTA. It's doing that because it's going in order. So the first thing, it prints hello world. It's still doing that. The next thing it does is it stores my DNA as the DNA string starting with A. The next thing it does is it prints that sequence. At this point in the program, the variable is still holding the value ATCG. We can then reassign the MyDNA variable to something different, but that doesn't impact what happened above it, right? We're going, the order of operations matters. So now, if we print MyDNA again, now we get the different variable, the new thing that MyDNA represents. So it's like a bucket. We took one thing out of the bucket and we put a new thing in. So it's just a container that we can swap out what is in the container. Also, like shell scripting, variable names are totally arbitrary. We could name this variable banana and it would work fine. We could name this variable elephant and it would work fine. Would that be helpful? No, that would not be helpful for going back and reading the code and trying to figure out what somebody was trying to do, what you were trying to do when you wrote the code. Naming variables something meaningful is, it's really important. So don't name your variable something random, as cute as it may be. There's like common variable names, foo and like all computer science examples, when you pick up a computer science textbook, are always variables named like foo and bar, I think. But we're gonna learn to start using good variable names from the get-go. Okay, so there are some rules to variable names that are worth knowing. You can use letters, numbers, and underscores, but it has to start with a letter. So it can be MyDNA1, it cannot be one MyDNA. So letters, numbers, underscores, no special characters. Don't try to use a %, don't try to use a period, don't try to use any of that. And always start with a letter. Capital letters are fine. And capital letters can start a variable name. That's not a problem. As long as it's a letter at the beginning, you're good to go. You are not allowed to, I said you can't start a name with a number, so don't try to put 7 as the first thing unless you spell it out, S-E-V-E-N. You can't use a word that's already built into the Python language. You're not generally going to run into this too much, but like don't use the word print as a variable name, because Python's just going to get confused and try to print instead of access the variable name to print. And there are lists online of all the like reserved words in Python. For the most part, just name it something that says what the variable is, and it's unlikely to also be a word in the Python language that does something. So case sensitive, if this were my underscore capital D, capital N, capital A, that would be a totally different variable. So your variable names are case sensitive. Okay, concatenation. I'm just gonna delete all this stuff. So the word concatenation means basically to stick two things together. We are going to use the adding symbol, and it's not adding in the sense of numerical adding. When you take a string and you add it to another string, it is not a mathematical operation. It's literally just sticking the two things together. So this might be easier if I make these two very different things, so it's easy to see what's happening. So in this case, that's why we call it concatenation instead of addition. It's more like just sticking two things together. Now, if we print. So it's printing TTTTAAAA. What we did here was take one string and concatenate it to another string. That concatenated whole, that new string of 8 characters, is getting stored in the variable called myDNA. MyDNA does not know that the concatenation exists. It does not care. Again, it's an order of operations thing. The concatenation happens, it returns a string of 8 characters, and that's what's being stored in myDNA. So when you print it, that's what you see. You don't see the plus, you don't see, it's just like one string exists. We can add, so let's say we had my T's, and then we want to have my A's, and then we want to have my DNA. So this is the power of variables. We can reuse them and use them for lots of different things. So this is saying, take the string that is represented by my T's, add it or concatenate it to the string represented by my A's, put that whole result into a variable called myDNA, and then print myDNA. So in this case, I'm sure you guys are all confident in what's going to happen here. But again, we're going to get the same answer. So even though there were a couple extra steps, we created some new variables. It works just the same. When we use a variable, it acts just like the string is there in its place. You can also do mixed addition. So my DNA2 equals my T's plus some other stuff. And then if we print my DNA2, so in this case, I'm taking a variable, my T's, that holds TTT. I'm concatenating it to a string that says some other stuff, and storing that into a variable called myDNA2. And then I'm going to print myDNA2 and see what it looks like. So this time it took the T's and it concatenated them to some other stuff, misspelled. And it doesn't add a space. If you didn't put a space inside the string, Python isn't going to add it for you. It's whatever is in between those quotes is what's going to get shoved into the variable. Any questions so far? Is this kind of making sense? Okay. We can do 3 additions. We can reuse variables. Let's get rid of that. So I'm going to do my T's plus my A's plus my T's. And this time my T's, and then the A's, and then more T's. I was able to reuse that variable again. It's also okay to do things, so you can nest operations inside of other operations. Again, this is very much like learning math, like learning algebra. You put things inside of parentheses and you can interpret, you know, the addition and then multiply it to something else. And so you're nesting things and doing lots of things in one big operation. So we can do that here too. So we can just put all of that inside of the print statement. And in this case, Python is going to interpret my T's plus my A's plus my T's. It's going to create that string that has 12 characters. And then that is going to become the argument to the print function. So print is going to print what that has kind of resolved to. So again, very much like order of operations in math. Once you do one thing, once you get that number, you do the next thing. In this case, you're going to get the concatenation happening inside. That's going to create a string. And then that's what's going to get passed to print as the argument. So that works great. And we'll see a lot of this nesting. You can nest lots of operations in Python. It can get kind of crazy. I actually prefer to write code that is longer but really clear. as opposed to nesting like eight things into one line of code, because it can get very, it's difficult to debug, it's difficult to interpret, it's difficult to understand. It's easier to just use lots of variables and do things in like a super clear, tiny incremental steps on every line. But sometimes, especially when you're using other people's Python code, you might see a lot of things nested. So another good thing to learn is the length function called just len. So in this case, we get to use a new return value. So previously, we've been working with strings. This is going to return an integer. So this will actually, let's just run it and see. Oops. We don't get any extra output. We also don't get an error. So that implies, okay, my length function is working, but this is kind of similar to adding things and putting into a new variable. What are you gonna do with it, right? It's the computer is calculating the length, but it doesn't have anything to do with that value. Do you want me to print it? Do you want me to add it to something? What do you want me to do with it? So to see it, we would actually have to print it out. To print it out, we might wanna store it in a variable. So since len is the key function, we can name the variable name length, and we know that won't have a name collision with the len function. And then we can print it. In this case, we get 4. So the length of the string inside the variable my t's is 4 characters. Okay, so Python treats strings and numbers differently. And it turns out the print function knows how to print a number. The print function also knows how to print a string, but something like the concatenate function is not going to really know what to do with this. So let's say we want to create a new variable called sentence, and we'll say my t's plus length. So we're adding a string to an integer. And it's going to say, no, 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 no. I don't know. Addition can be used numerically to add integers, or it can be used to concatenate strings, but I don't know what adding a string to an integer means. Like, what do you mean by that? And what it actually says is type error must be string, not int. So we started with a string. It gets to this and it says, okay, that's definitely concatenation. What do we do when we use a plus sign with strings? We concatenate. And then it gets to this and it says, that's not a string. I don't know what you want me to do with that. Error. So Python will allow you to convert things into other things. And fortunately, there's a very easy way to convert a number to a string. And it's the str function. So if we wrap this in a function called str, so what this is going to do is it's going to take the length integer, put it into this function. This function is going to turn it into a string and return the string. And so then we'll have a string plus a string, which we know is concatenation, and we'll get what we want. And of course, this is just going to sort in sentence. We want to see what sentence actually is. We'll have to print it out. Now we get our TTTT4. So we were able to concatenate a 4 onto the end of the string, and now the 4 is it's a character in a string. It's no longer an integer. We couldn't take that sentence and add 7 to it and expect to get TTT11, right? Like, you're either a string or you're an integer. You cannot be both at the same time. So that's important to understand. So we can do this inside the print statement as well. Let's see, what would be the easiest way to do this? So you'll see this pretty frequently. Now, in this case, we're going to have nested parentheses, right? So this parentheses goes with that one. Those two are pairs. So what's going to close this one? We have to put another parentheses at the very end, like that. So again, order of operations, this is going to interpret it. The integer is going to get turned into a string, concatenated to this other string, and then this whole thing is going to get printed out. And it still works. Okay, so now let's learn about methods. So functions and methods are actually, they look similar, they act similar, but they're syntactically different. So a function is built into the Python language. It can operate on many different types of things. Like the print statement knows how to print a number, it knows how an integer, it knows how to print a string, it knows how to print when we get into arrays, it knows how to do lots of things. So it's a core part of the Python language. A method is something that belongs to a particular type. So a method can only be used on one type of thing. The method we're gonna learn now is, what's the first one we learn? Lowercase. Let's make things lowercase. And that's a really good one to start with, because making a number lowercase, like, what would that even mean? I don't know. So it's not, lower is a method that belongs to the type string. So it does not belong to everything. You can't lowercase anything. You can only lowercase a string. So let me get us some clear space here. So we're going to start with our simple string, and then we'll add a comment, print in lowercase. So in this case, a method is different because you take the thing that is the type that the method knows about, put a period, and then you put the method. Similar to a function, it will have parentheses. So it will have parentheses, it can accept arguments. But instead of hanging out on its own, like print just lives on its own. Print's like, hey, I'm print, I can print anything. Whereas lower has to be associated with a string. To tell it what string to be associated with, you put the name of the string, so like the variable name, you put a period, and then you put the method, and then you put your parentheses. And if you need some stuff in the parentheses as arguments, that's fine. But that's the difference, is it's almost like it has to be attached to a thing. It needs to be attached to a type of thing that it can operate on. So print is the function, but inside we have a string with the method lower. And it made our t's lowercase, so it worked. Importantly, a method does not change the nature of the object. So lower is not changing the nature of the variable myT's. If we print myT's, it's still going to be uppercase. Nope, prints is not defined. If we do that without misspellings, we're back to the capital T's. So let's talk about that for a second. So myT's.lower takes the string, makes it lowercase, returns a new string that's all lowercase t's, and that's what gets printed. It does not go into the myT's variable, the bucket that is myT's, and alter the nature of it. It is not making any sort of permanent change to the variable. It is taking it, operating on it, and returning something new. We can actually save that in a variable of its own. So that is that. We could call it myT's lower. So now we have two variables. The first variable still holds capital T's. We took those capital T's, we made them lower with a method, and we stored that into a new variable called myT's lower. And we're going to print that. Makes sense? So we get the capital T's, and then we get the lowercase t's. So the method to save the results of that method, you need to put it into a new variable. Okay, let's see what happens if we try to use a method on something that is not, it's not meant to work on. So let's just get an integer. We'll call it my number. And we know len, that's the thing we've learned that can give us, that will return an integer. The len function always returns an integer. And then what if we try to use lower on it? So we expect it to be 5, and we're saying 5.lower. In this case, we get the attribute error. Int object has no attribute lower. So that's basically saying it has no method lower. So if you see this error, that's what that means. It means that's not a thing I know how to do to an integer. Lower is not part of my vocabulary for integer. Not surprisingly, there is another method called upper. Upper makes things uppercase. It operates also on strings. I'm sure you guys are not super surprised by that. Okay, so another good useful method that we can learn is replace. Replace is an example of a method that takes 2 strings. So it requires string to operate on, and then it takes all of the occurrences of the first argument and replaces it with the second argument, which is probably going to be a lot more clear if I show you an example. We'll just start fresh. Okay, let's create a new variable called protein. LSPADKTNB. So we'll just type some amino acids. And let's say replace valine with tyrosine and do protein. So what is the string we want to operate on? What is our starting point? Our starting point is the protein. The method we want to use is replace. First argument is going to be the valine. We want to take all of the instances of V and replace them with Y's. And since we have 2 open parentheses, we need another closed parenthesis so that it's balanced. So again, the string has the method replace. The method replace takes 2 arguments. The first argument is the thing to replace. The second argument is the thing to replace it with. So turn all the V's into Y's and print the whole mess. So in this case, we get our string printed out, but it has Y's instead of V's. You can see there was a V at the beginning and end when we started. When we printed it, there was a Y at the beginning and the end. Again, this is not changing the intrinsic nature of the protein variable. The protein variable, if we print it, still has B, L, S, P, A, D, K, T, and V. Like it's printing within this argument. The protein is going, the method is replacing V's with W's, returning a new string, and that's what's getting printed. Yep.
So the comment comes after accept, or you could begin with basically tyrosine and
the comment can go anywhere. We can say like this, the £sign comments. Yeah. We can put lots of comments everywhere. We can even put it at the end of lines. I mean, you can put them everywhere. All of that's going to work fine, right? So put like the protein replace down below.
Yes.
Sure. Yes. so that'll work fine. So what if I, and actually another thing you can do, let's say we don't want to do this anymore. Let's just comment that out. So now none of that line's going to get run. So the only two pieces of code that are going to get interpreted are protein equals this. So we're setting up a string and we're doing a replacement. If I run this, what's going to happen? Nothing. There's what do you, okay, great. I replaced these things in the string. What do you want me to do with it? Do you want me to print it? What do you want me to make it uppercase? Like, tell me what to do with it. So in this case, we could store it in a variable. So we'll call it tyros. And then we can print tyros. And now we'll be able to see what it's doing. Right, so control. So it's printing the replaced version, right? So, and if I print, okay, so I'm going to print the tyros. I'm going to print the word original colon, and then I'm going to print the original protein variable. So it'll print the replaced one, and then the word original, and then the original one, like that. There's a lot of this in the homework, so let's work on that for a second. We can put replaced version, colon space, and concatenate it, and original. So in this case, I'm gonna have, and again, I'm mixing single and double quotes. It doesn't matter as long as the string, as long as it's flanked on either side by the same, right? You can't do a single and a double or a double and a single. As long as there's a single and a single, that's gonna be fine, or a double and a double, that's gonna be fine, yeah.
Can you, when you're doing the plus tyros, can you do the backslash n to put it in the next line?
Yeah. Okay, so yeah, let's try that. So let's save it and do it this way once. Replaced version and the original version. You can see they're different. Our V's got turned into Y's. And then we could put the slash n's here. Or we can even put it before the space, and you can see where the space ends up. So that's, anytime you put a slash n inside a string, has to be inside a string, it will add a new line right there. And in this case, it was a new line and then a space, and then the variable, so the space got printed in front of that V. See, I left a space here. So that space gets printed before the protein variable gets printed. Does that help kind of explain?
So that space goes to the next line.
Yes. So it prints the word original, it prints a colon, it prints a new line, it prints a space, and then it starts printing the protein. The new line occurs wherever you put the slash n. Another fun thing. So we can get substrings, which are little tiny bits of strings that come out of big, larger strings. And substring is just like a common word you hear in computer science, but just means a piece, like a smaller quantity of a string. So let me get rid of all this mess. Okay, so the way we work on strings is with indices. And this is kind of like we've been learning about with SNPs. You're saying, oh, the SNP occurs at base 63. So you know it's like the 63rd letter into the sequence of letters. Python throws a little kink in the plan, because it is a zero-based indexing system. So let's take the word banana. This is sequence character 0, 2, 3, 4, 5. So even though it is 6 characters long, it starts from 0. And the 6th character is actually index 5. So this is probably one of the most frustrating things about Python for bioinformaticists, because all of our software numbers things starting at 1, because that's what sensible people in the world do. Python, on the other hand, starts numbering at 0. So you're constantly trying to fix your code so that if you say a snip is at position 1, if Python tells you a snip is at position 1, you're going to add 1 and say snip is at position 2. Because duh, 1, 2, 3, 4. But so be on the lookout for that. Lots of errors from that. So the way we get little pieces of a string is like this. Little notation. So we're saying, and this is where we're going to start using square brackets. And this is a larger structure that we will maybe or maybe not get to, depending on how far we get through the book. But basically we're saying starting from index 3 and going to index 5, get that part of the protein string and print it. Okay, so we only got PA, which is a little bit counterintuitive. So this was 0, 1, 2, 3. So we got 3 and we got 4, but we didn't get 5. Why is that? Well, again, because Python is very strange, and the first number is inclusive and the second number is exclusive. It's something you have to memorize. So 3 to 5 would say, okay, we're going to start counting at 0. When we get to 3, I'm going to include that. And when I get to 5, I'm going to exclude that. Inclusive, exclusive. Don't ask me why. This is actually probably my absolute total least favorite thing about this language, is that I think indexing is done in a really stupid manner. But that's how it works. So you just have to memorize that. Position start is 0. So if we want to get the first base, we have to start at 0. So actually we can and then we can make this even more helpful. Okay, so we're going to print the original string. We're going to print a little note to ourselves that we're looking at indexes 3 to 5 and print what is that substring. Print another little note to ourselves saying we want to look at the indexes from 0 to 5, and then we're going to print that substring. Okay, so 3 to 5 is PA, so 0, 1, 2, 3, 4, exclude 5. Where 0 to 5 is 0, 1, 2, 3, 4, exclude 5. That's strange, I know. It's a weird way to do things. What's another thing we can, oh, if we just make up a really long, like 0 to 60, our protein is not 60 characters long, but what happens if we do that? In this case, it just prints to the end. So if you give it an index that is way out past the last base, it just stops at the end. This is very different. I don't know how many of you have been dabbling in R, but R starts over. So it's a really weird R thing that it'll just start like printing back from the beginning. Python's not going to do that. It just stops at the end. We can also use, we can get a single character by just printing, by doing another number, like just one number. So we'll do character 1. In this case, since there isn't a range, like the first one's always inclusive, so you just get the one character. So 0, 1 is the L, so you get the L. What are other things you can do with ranges? We can do, oh, okay. So I've been using colons as part of my labels, but what if we did 1 colon with no end? So like this. So I'm saying I'm going to use 1 colon. What does that give me without a number? It gives you the whole thing. So if you just refuse to put the last index, it just goes all the way to the end. So if you don't know how long the string is and you're too lazy to get the length and put in a variable and put that into the little square brackets, the easier way to do that is just put colon until the end. It's basically colon nothing is colon until the end. So inclusive at the start, exclusive at the end. We can count the number of times a substring occurs in a string. We can use that with the count method. Again, this is a method that only operates on strings. So count the valines. So in this case, I'm just going to use the count. So the replace used 2 arguments. Count only uses 1. It says take the string, the very first string that I give you, count for the occurrence of this new string that I give you as an argument, and return that number. And then I'm just going to print it so we can see what it is. So we have 2. You can count longer strings. So we could say just count equals protein.count VLS. I don't think I have anything that occurs twice. Let's put VLS at the end then. Okay, so protein count VLS and then print. Yeah. So we get 2 again. But what if I put VLS, VLS, VLS? Okay. I'm going to put a whole bunch in there to see, should correctly count them. So 5, because I added a bunch of V's and a bunch of VLS's, so it's counting both. So that is a super simple, you can also have, well, that's 410, we'll leave it there. So the only thing we didn't manage to get through in this lesson is binding. And you might or might not need that for the homework, I'm not sure. But it's all online. Go to the Python for Biologists website. We've gone through almost everything you need for the homework. The last thing is a find command, which I'm sure you can figure out what it does. It finds a substring and it returns the index. So if I said find in, it's going to return a 2. Or find A, it's going to return a 1. So practice that and take a look at the homework. And I'll see you guys next week. Unless there's any questions. Anybody have questions? All right, thank you.